Hi, welcome to me313, Mechanical Engineering Thermodynamics. The topic of this video is multi-stage compression refrigeration, and the section of the textbook is 11.8. Here are the three learning outcomes. At the end of this, you'll know the major components that comprise a multi-stage refrigeration system. You'll understand the similarity and the differences compared to cascade refrigeration, and you'll be able to solve for the conditions in the multi-stage refrigeration system. So here's a diagram of multi-stage refrigeration, and it looks fairly similar to cascade, but it is also very different. First of all, we don't have two separate loops. We have a single loop. We have a single type of working fluid in it. We again have two compressors that are operating between a low and a medium pressure, a medium and a high. But instead of running two separate cycles completely, what we have is what's called a flash tank, it's a separator, that after running through a throttling valve, the liquid goes through the bottom and the vapor comes over to the right. So what that means is that going through the colder temperature, where after we run through the second throttling valve, is only going to be a fraction Y of the complete material that's operating through the upper stages of the cycle, right? So one of the things that makes this a little different is that you can actually, it's a little simpler because there's only one type of fluid that you need to run through. And since this bottom stage compressor is only running the fraction Y, it often has a lower power requirement. However, they tend to be fairly similar to cascade refrigeration, and you'll see both types used depending on the particular temperatures that are necessary for the application. So let's go ahead and look at this on a TS diagram. And so I'm going to start off looking at the bottom stage. And I'm going, for example, 7 to 8 to 1. And so 7 is a saturated liquid going through an isenthalpic stage, 2.8. Absorbing heat, if we assume it's ideal, we would go over to 0.1, and then if it was an isentropic compressor, that would be up at 0.2. All right. Now let's go ahead and look at what happens. We've got 0.3, which is the saturated vapor that is in equilibrium with 7. So that's going to be straight across over there. That's going to be 0.3. 3 and 2 are mixing with 9. So I have a saturated vapor and a superheated vapor mixing together. It's going to be some point in between. So 0.9, you know, it's going to be somewhere in between those two on the same isobar. So this is all over here is an isobar. And then 0.9, if it was goes through a compressor, I'll again draw it straight up to be isentropic. 0.4, and then this is my high pressure going over 2.5. and then running through a throttling valve down to that middle pressure. So there, right there, is going to be 0.6. Recognize 0.6, right? The liquid's going over to 0.7, and the vapor's going over to 0.3. We look at the cooling capacity, and again is represented by the area on the bottom down here. And so we can again see it's a little bit better than if we had a single stage compression, like a typical vapor compression refrigeration. Although also remember, we need to weight this area here by the fraction Y. So we do a kind of an apples-to-apples comparison. But there's also a reduction in the work requirement, which is a reduction in the area up there. And that we don't need to weight by Y because that's going to be all done at the high stage compression. So again, we'll find out the coefficient of performance for this cycle tends to be better than it is for a single stage vapor compression refrigeration. So I'm going to go ahead and again, I'll do the example in the book, but I'll do it using EES. And so here's the equation in EES. And so we're doing the same one we've done in the last couple of videos, the same parameters. So I'll go through this fairly quickly. Again, I'm using R134A. I defined a string variable with it. Here's my low, medium, and high pressures that I have defined. And then I've got my isobaric steps. I have two throttling valves where I've got my equation equating the enthalpy. And then I'm assuming that both of my compressors are isentropic. And then the last thing that I've done down here and added is in the flash chamber, I have just what the enthalpy is at 0.3. So if I go ahead and attempt to solve that, I find out I'm actually undefined. I need an additional equation. And so you might wonder what equation I need. And the equation I need is I need to do that mixing chamber. That's going to actually determine what the fraction of material is that I have. So let me go ahead and add that equation. And so if you look at it, here's the mixing chamber equation, and it just says that the fraction H3 of Y and 1 minus Y of H2 is H9. Then I can go ahead and solve it. And now if we go ahead and look at our equations, our rate table, we have pressures. All of our pressures, we have several entropies, and where we don't have an entropy value, we have an enthalpy value. So the problem is completely specified. We can go ahead and complete to solve the problem. Let's go back now and find out what our coefficient of performance is. And so again, looking at the new equations that I've added, my work input, I've got two compressors. The low stage compressor I weight by 1 minus y, and the upper stage is the full mass flow rate m. And so this is an extensive work. Here's my heat going into the cycle, Q low. Again, I need to weight it by 1 minus y because only a fraction of the material is at the low stage. So that's going to be a lower QL. And then I can find my coefficient of performance, desired over required, QL over W. And I need to calculate a couple more enthalpy values to go ahead and complete that. So now if I come over and look at my coefficient of performance, I see it's 4.476, which is essentially about the same as the cascade refrigeration cycle. So, and that's pretty typical. You'll find cascade refrigeration and multi-stage refrigeration have similar coefficients of performance, which means the same QL for a given work input. And so the determination about which one you want to use is going to be what the particular temperatures are that you're operating at, what the desired use of that refrigerator is, and maybe what the component costs are. They both require two compressors, but those compressors are going to be running at different mass flow rates. So it kind of gets down into an engineering calculations and economics problem to determine which of the two you would prefer to use.